at the University of Florida's Florida Museum of Natural History, and I study paleobotany or fossil plants under Dr. Stephen Manchester. And today I will be presenting my dissertation defense. And this is right before the dissertation defense. So tomorrow is the actual day, but I'm sharing the lecture with you guys a little bit early, so you get the preview. It's going to be the exact same thing, but it is a kind of a special access preview. So today we're going to be talking about climate and diversity of the early and middle Eocene floras from middle latitudes of the Northern Hemisphere. So the Eocene is a time that's about 55 to 35 million years ago, and I'll really be focusing on a range of about 50 to roughly 40 million years ago. We'll actually narrow it down a little bit as we get further in the talk. And I forgot to start my timer because I want to make sure that I'm on time tomorrow. I know I have a little bit more flexibility here. All right, so of course, I think as most dissertations go, they never go completely according to plan. I had initially thought I was just going to be doing the Clarno Formation, and then Steve and I ended up stumbling across a formation called the Kishinine. It was this similar age to some of the fossils that we find in the Clarno. So we thought, oh, you know, this will be a nice, quick pandemic project that we can get out. We thought there were only going to be 15 or so different species of plants, but it turns out to be one of the most diverse Eocene lake lacustrine sites in North America. So this ended up being a full chapter. So of course, I mentioned Clarno earlier. So this is a formation in Oregon, and we'll be looking at the pollen or the polynomorphs from the Clarno Formation. Polynomorph is a term that we use to collectively describe both spores and pollens from plants, since they're made out of the same substance. And when you process rock for them, you get them in the sample. We'll then be looking at fossil leaves from the nut beds, which is a specific locality in the Clarno Formation. We'll then be heading over a little bit northeast over to northwestern Montana. And then we'll be looking at the beta diversity of Lutetian. So beta diversity is the difference in biodiversity between two different sites. And Lutetian, that is a time within the Eocene. That's a stage within the Eocene that's roughly 48 to 41 million years ago. So let's start off with the formation of the Clarno Formation. So this was deposited as the Farallon and Kula plates were subducting under the North America plate. Of course, this caused a lot of volcanism, and the lava and ash that resulted, that helped lay down part of the formation. But we also get lake deposits in the streams that feed into those lakes as part of this formation as well. So this starts from about 54 million years ago all the way up to 39 million years ago. And a lot of the fossils are part of the John Day Fossil Beds National Monument, but of course there's many other outcroppings of the Clarno that are outside of the monument as well. So some of the units that you might have heard of if you've been over to John Day would include the Fern Quarry, Hancock Canyon, the Nut Beds, and then also the Mammal Quarry, which sits on top of the nut beds, or above the nut beds, I should say. And on the left, we have a picture of what that outcrop looks like. From this locality, we know of a few vertebrate specimens. There's about 6 species of vertebrates total. We have a crocodilian called Boverasuchus. We have a turtle. We have an early carnivore called a creodont, as well as some early rhinos and horses and rhino relatives. And of course, this site is called the nut beds, and that's because of the diverse fruits and seeds that we find there. And collectively, we often call fruits and seeds disseminule. So you'll hear me use that word a lot through this presentation. One of the most charismatic disseminules that we find are these incente or banana seeds, because we don't usually think of bananas growing in Oregon today. We also have these menisperm seeds, or the moon seed family, because they're shaped like a crescent moon. The oldest walnuts are known from the nut beds. This is Juglans clarnoensis. Juglans is the genus for walnut. And then we also have another subtropical to tropical family called Icacinaceae. And this is the endocarp, so sort of like a cherry or apricot pit, except it has these little circles on it, and these actually invaginate into the inside of the endocarp. So it's just a very nice looking endocarp. Now, there is some debate about the age of the nutbeds. The most commonly cited age is about 44.3 million years old, and this is backed up by radiometric dates. But another date that's less cited is 48.32. This is also backed up by radiometric dates, but also backed up by the mammals that we find there. So we can compare the age of the mammals to the what we're seeing at the site, and that happens to be 48 or roughly 48 million years ago. There's also some debate about what type of depositional environment this is, whether this is a stream or river flowing into a lake or a volcanic flow. Of course, those aren't necessarily independent of one another. You can have volcanic flows following a stream or river flow as well. So not independent, but they could also be separate. All right, so in addition to the nutbeds, we're looking at two other sites that are south of the nutbeds. Those are White Cliffs Jr. and Red Gap. Of course, these are both in Central Oregon. White Cliffs, just as kind of a fun aside, actually used to be property of the Rajneeshpuram, and you can see some of the evidence still there today. So interesting little bit of history. Of course, today it is a young life camp. So why are we looking at pollen? Well, they could show us something different than what the fruits and seeds and wood and leaves can show us. And the other nice thing is that we can get a very large sample size relatively easy. We can get well over 100 pollen grains in a slide. So it's very easy to do statistical analysis with pollen. But of course, we have to start somewhere, and that's what do we have? So in order to actually find pollen, because pollen's really small, we have to process the rock. And so what we'll do is we'll cut it up, we'll macerate it, so we'll make it into more of a powder, then we'll dissolve it in acids and bases, and we'll use Darvan to help separate the pollen out. And in between each of these steps, we have to add water and centrifuge it down because we don't want the acid and the base reacting directly with one another. Some of these we did in the lab at University of Florida, but others we sent off to Canada, and others past students have done for projects that they've worked on. In terms of imaging, so yeah, once we have the sample, it ends up being a little solution, and we can put some drops on a light microscope slide and look under a light microscope, or what we can do is we can put it on a little stub and coat it with some sort of metal alloy and look under a scanning electron microscope. And they'll show us different features of the pollen in order to help identify what it is. And that's what a scanning electron microscope looks like. So pollen is readily identifiable. At least we can tell, one unit is different from another. So we can tell by its size, its shape, which could be flat like a frisbee, orb-like like a basketball, or it could be more prolate like a football. They can have different types of apertures or openings. So they might have holes, they might have slits, or they might have a combination. And they could have different sculptures or textures. Another way of saying it would be ornamentation. So they could be completely smooth, which we would call silate, or they can have microechini, which are little tiny spiky projections coming out of them. And a whole variety of combinations for these plant parts. So we do have some ferns. On the left, we have a monolete spore. On the right, we have probably a monolete spore as well. There's some junk on the SEM photo that's sort of covering up the aperture, so it's kind of hard to see, and it looks like there might be the size of the ornamentation might be a little bit different. We do have the first occurrence, or excuse me, not first occurrence, but the first recording of Cyperaceae, so the sedge family, Poaceae, the grass family, and Typhaceae, the cattail family for the Clarno Formation. So we have those three. My favorite grain that I found is this Parthenocissus grain. I just find it a very beautiful specimen. So it has this reticulate sculpture, and it's trichoporate, and so you can see that there's a ridge, and then there's a little pore in the middle of the, excuse me, not ridge, but the slit. Um, Parthenocissus is not a genus that we have in the Pacific Northwest today. This is in the East Coast and other parts of the world, but it is a vine, and it's part of the grape family. We have many representatives of the walnut family of Jugundaceae. We have this Caria pollinites. So Caria is also known as hickory or pecan. We can tell it's that because it has these three pores that are on one side of the grain. We also have juglans or walnut, which we would expect because we have the macrofossils of juglans. We also have a lot of members of the birch family, Betulaceae. This is sort of a generic grain that you can find called Tripropollinites, corloides. We don't know which plant or which plants within the birch family it belongs to, and it could be an extinct plant as well. More than likely, it's an extinct plant. But we do know specifically what this comes from is this grain down here. This is Ulmus clarnoensis. This is an alder found in the Clarno Formation. And we know specifically that this grain goes with this plant because Stephen and others have extracted the pollen from the catkins. And so not only can you extract pollen from just bulk rock, but you can also extract it from the flowers, potentially from fossil flowers that you found, which is what happened in this case. Probably the biggest, at least, surprise was the finding of these grains. This is irregularly shaped, and then if we look in the top right here, we can see these little strings, and these are called Vicin threads. They help pollen clump together. And the combination of this shape and the presence of these Vicin threads help us identify this as Oenograceae, which you might know as the fuchsia family that contains fuchsias. All right, so that's obviously not everything that we have, but kind of the important or interesting things that we have. So how do these all compare to one another? So at Red Gap, we had 55 OTUs, which stands for Operational Taxonomic Units. It's not exactly species, but it's just a way of working with taxa without constraining yourself to a certain phylogenetic or taxonomic standing. So the most common grain here were just things that we couldn't ID at all. They were just gunky and destroyed. But the next most common thing that we found was walnut pollen. And there's a bunch of names on the bottom of the screen right here. It might look like they're zeros, but they usually just have one or two grains, and they just don't show on the scaling of the graph. At White Cliffs Jr., we had 29 operational taxonomic units, with the most common being grains that we could tell were from the birch family, but we don't know exactly which genus, which member of the birch family they belong to. And at the nut beds, we had 31 OTUs. Unidentifiable grains being the most common, followed by this grain right here, which we dubbed monosulcate silate. So it has one slit through it, and it's silate, so it's very smooth, but we don't know which plant it belongs to because it's sort of a generic looking pollen grain. All right, so are these sites statistically different than one another? That we can't get at directly, because to do that, we would need to do a chi-square, and with a chi-square, you divide by an expected value, and we would have zeros at some of these sites, and you can't divide by zero. So we have to get at it some other ways. So one thing that we can do, not statistical, but in order just to look at the comparison, is we can look at the abundance data from all of these sites and use what's called the Bray-Curtis dissimilarity index. And when we do that, when we do all those pairwise comparisons, we can see that these are pretty high, which means that they're really not that similar. And we might want to sort of disregard abundance for two reasons. Different plants produce different amounts of pollen, and you also might have plants that are at different distances away from the depositional source. So the thought being that if you're further away from the depositional source, you're not going to be as well preserved. And so when we do that using this Sorensen dissimilarity index, we still get relatively high dissimilarity values. So they're not all that similar. All right, so to actually put in some stats into this, what I did is I decided to test and see if maybe geographic distance plays a role, since we have one that's further away and two that are closer to each other. And we can test to see with a Mantel test, a test to see if there's either some sort of linear relationship or just if there's some sort of positive or negative relationship. And that could be logarithmic, it could be exponential. It just does a relationship exist? And when we do that, we have these high p-values. All are higher than 0.05. So geographic distance is not playing a role into the dissimilarities that we see. Now, one contributing factor could be that these are being deposited at different times. We're not exactly certain of the age of the nut beds, and so it could be very well that this is, almost 2 million years or 2 million years older than the rest. And definitely, certainly, these are not coming from the same lenses. And so, any matter of time between, a year or 2 million years could have passed between these samples. But regardless, I would argue that these do represent at least some sort of end member or possibility that these communities can change to over time. And that's likely because it's not just the abundance that we see, but we also see it in the difference of the presence and absence of different taxa. The differences that we see are actually these are more different than the majority of the sites that we see in Colorado surrounding the Eocene and Oligocene transitions, with one exception, and that could be because of elevation. One of the sites was hyper diverse, and the other site wasn't so diverse, and it could be at a higher elevation. To wrap up what we've done taxonomically, though, new to the nut beds are Oenograceae, the sedges, and grasses. And to red gap, we have the sedges, grasses, and the cattails. And lastly, one sort of thing of interesting note is that we had very low counts of conifer grains and fern spores, and well, just spores in general. No lycopodium, no lycopods, so no club mosses, no ferns, no equisetum. This could be because some of these plants are indicative of disturbance, and we might have low disturbance at these environments at time of deposition. But that's one interpretation. We know there's volcanism in the area, so it could just be that this got deposited in time when a volcano wasn't immediately erupting, but that's still to be determined. So we're going to focus just on the nut beds now and look specifically at the leaves. And of course, we have the same question: what's present? And how does this differ from what we already know? So we have 173 different dissimulus described. This is the most diverse Eocene wood site in the entire world, with 76 species described. That was done by Steve and Elizabeth Wheeler. And then there's a total of 39 polymorphs. And from a previous slide, I said there's 31. That's because that was from that count. So I did a preliminary count, and some of those taxa didn't appear on the secondary official count. Lastly, leaves can tell us a little bit about the climate. And there's two different ways that we can, two main ways that we can tell about climate from fossils. If we're looking at things like mean annual temperature and precipitation, mean annual precipitation. So one is through what's called a coexistence approach. So looking at the species that we have, looking at what their modern relatives are and their climatic ranges and seeing where they overlap. And then another broad array of estimates are leaf physiognomy estimates. And so that's looking at the physical traits of leaves and using those to calculate different climatic parameters. So in the past, people have looked at the nut beds before, and there's a lot of text here, so I'm not going to read everything one by one, but people have looked at using singular linear regression models multiple linear regression models. They've used something called CLAMP, which I'll get into more later. And they've used two different models looking at the characters that they see in the woods. The main takeaway here is that the lowest estimate is 9.2 degrees Celsius, and that the highest estimate that we have is 18.8 degrees Celsius, which has appeared twice in this multiple linear regression model and also one of these wood models. But there is a bit of variation in these studies, and our highest estimate is over twice the estimate of the lowest. So two methods that I used were leaf margin analysis. This looks at the percentage of entire margin leaves versus tooth leaves in the assemblage. And the more entire margin, or the larger the proportion of the entire margin leaves that we have, the warmer the climate is. And the leading idea of why we think that is because tooth leaves often grow in colder or cooler climates. And so when the growing season starts, they need to take in more CO2 quickly. And we think the teeth of the leaf help with that intake of CO2 in the early growing season. The other method I use, that's a linear regression model. So that's a simple line. The other method I used was called Climate Leaf Analysis Multivariate Program, which is just CLAMP. This is a canonical approach. So it's a multidimensional approach. It uses 36 characters on a leaf. And these range from things like not only the presence or absence of teeth, but if they're near or far apart, if they are rounded or pointed, if they're compound or simple, the categorical size. So essentially it's like small, medium, and large, but we have some intermediaries and they're all defined by parameters. The shape of the apex and the base, the overall shape of the leaf, and then the length to width ratio of the leaf. What happens is we gather all these characters, we score the whole flora, and then we compare that to modern floras with known climates, and then we're able to infer what the climate is. And one of the nice things is we can use incomplete leaves with this method. So one of the downsides, though, is that we can only use what are called dicot leaves. So these are flowering plants that are not monocot. So nothing like ferns, or definitely not ferns, but no palms, no grasses, nothing like that. You would be able to use things like magnolia and sycamore, but no monocots. So in total, we found 127 different leaves. This is across all plant groups. And within the dicots, we found 119 morphotypes. This is compared to 74 morphotypes that were used for previous studies. And so some of the plants that we found is we were able to identify this fern as Seleptris with these veins kind of forming this triangle. We have three different species, or really three different genera of cycads. We have palm. We have members of the beech/oak family, and specifically we do have oak. We also have Paliures, so this is a member of the Rhamnaceae, which includes Paliuris as well as Jujube. We have three different species of Miliosma, and we would expect to find multiple species of this plant because there are 6 species that are known from the fruit. So go to figure that we would find a lot of different Miliosma leaves. We also have stuff in the willow family, although it's stuff that's found in the subtropics and the tropics, nothing like our temperate willows. Another member of the Rhamnaceae, Magnoliaceae, so Magnolia family, and then what could be a member of the Mallow family. We have Maginatea, which is this extinct sycamore, and I'll use this time to have a lab mate who's also defending. She'll be defending on Friday, and if you want to learn more about fossil sycamores, I can send you a link to her talk. Her defenses will be early in the morning, though, for the Pacific time. And lastly, we have what could be Elaeagnaceae, which has this very fine, these very fine free-ending veinlets in their leaves. So sadly, we actually have a very low completion score. We only have a completion score of 58.6%. So that means we're missing a lot of things like bases, leaf apices. We're not able to fully know how large the leaf is, and so that's not really good for our results. But let's take a look at them anyway. So we have mean annual temperature of 19.8 degrees Celsius. And then our growing season precipitation, that's what GSP is here, of 201 millimeters. For our leaf margin analysis, 61.1% of our leaves were entire margined. This is opposed to 52 that were described earlier. We plug and chug that into our equation, and then we get a mean annual temperature of 20 degrees Celsius. So both of these estimates are warmer than the estimates that we've had before, although they are relatively comparable, especially when you consider the error on clamp is 1.13 degrees. That definitely puts it down into that 18.8 range. And of course, that 18.8 estimate has an error bar too. So at least the errors are overlapping, and there is some consistency with these estimates. They are both in that higher part of that temperature spectrum that we saw from before. However, this does kind of bring up something interesting. So at the start of the talk, I was mentioning how we don't really know, or not that we don't know, but there's a debate about how old this site really is. And so if we look at global ocean temperature throughout time, this is the Zachos curve. And we're using this as a proxy for Earth's temperature. So if we look at where 48 million years ago was, we can see that the temperature was up here. And if we look down at 44 million years ago, the temperature of the Earth is down here. And there's almost a 4-degree difference between those two sites. So how old this flora is sort of affects our interpretation of, is this an outlier flora that has unique climatic conditions, or is this following sort of a global trend? When we compare it to regional floras, it almost falls, if we use the date of 48 million years ago, it almost falls perfectly between the Heron flora, which is almost 52 million years old, and the Arbuckle mountain flora, which, excuse me, both are Heron. So East Birch Creek versus Arbuckle Mountain, 52 versus roughly 44 million years ago. So the 48, that date falls in between there. Those temperature estimates fall in between there. We start looking for other floras that have a similar mean annual temperature, and some of the floras in the Puget group would meet our criteria. However, these floras are poorly dated and also poorly understudied. So we have evidence to support a 48 million year old age, but I would just argue it's evidence, not conclusive evidence that it is 48, because we're also using a bunch of other assumptions in our models for the temperature. And again, we don't really have good dates on some of the other floras that we could compare it to. I would argue our precipitation estimates are very unreliable. We had a growing season precipitation of 201 millimeters, and when we plot that against the temperature, it would mean this would be a desert. And we have some really large leaves, which usually indicate a wet climate. We also have things like Acacia and Menispermaceae, which, to my knowledge, don't grow in deserts today. So I would argue that because of our our low completion rate, missing things like apices and bases, that's what's really driving our unreliable results for precipitation. And then we also have, again, to recap, the diversity, we are adding Phyllopteris, Iliagnaceae, and Rhamnaceae to our understanding of the flora. We didn't know about these taxa from the other elements, from the diseminules. We didn't know about them from the wood or from the pollen. All right. I know there's a lot. So we're moving on to a little bit northeast of Oregon, up into the Kishinine flora of Montana. Now, this is a formation that stretches from southern British Columbia down into northwestern Montana. And unlike the nut beds, this is lacustrine shale, so a lake deposit. And this has been dated to about 44 million years ago. There's been a lot of studies on the various faunas from the Kishinine. So we have 37 terrestrial mollusks and 25 freshwater aquatic mollusks. Most famously, though, this formation is known for its insects. It has 15 different insect orders from it, and it's been hailed as a Lagerstraten. So there are 21 different fly families. So Diptera is the fly order. And mosquito is a type of fly. And in one of the mosquito fossils that's been found from the Kishanine, we actually have hemoglobin from its last blood meal. So we have really exceptional preservation in a lot of these fossils that we're finding from the shale. We also have fish, so a variety of vertebrates. We have fish, turtles, we have a crocodilian, and then also a wide variety of mammals, 26 species total. And not much has been done on the flora. There's been some work on the pollen on the British Columbia side of things, but nothing down in Montana, and also nothing on the macrofossils. So we're going to figure out what type of plants we have, and then also what the climate was like. So we have cupressaceous conifers. So this includes things like metasequoia and juniper, as well as some other members that we can put into the family and within the subfamily within there. But they could be anything from related to arbovita to incense cedar to western red cedar. We don't know. They're kind of hard to tell with the little fragments that we do have. We do have 6 different morphologies of pine seeds. We probably don't have 6 actual species of pine, but we do have at least 2 different species of pine. And we know that because we have both subgenera of pine present. So we have Pinus subgenus strobus, which has a disarticulated seed body from the wing, and also Pinus subgenus pinus, which has an articulated seed body to the wing. Probably one of Steve and I's, one of our favorite things about this site are the aquatic plants. And on the left, we have Spirodella. This is a type of duckweed. And we know for sure it's Spirodella because we have all of these little pigment cells that have been preserved. So this is one of the ways to tell it apart from Lemna, which is another genus of duckweed. So the presence of these dots is what really helps us nail our identification down. We may have the oldest Wolfiella, which is another duckweed. It's sort of hard to interpret with this picture, but what's happening here is there's actually 4 plants here. So this plant is asexual reproducing, and so is this one. So there's 1, 2, 3, 4. This is what we interpret as the brooding pouch, or where the asexual propagules come from Wolfiella. All right, so our most common fossil from this locality are these Carpolithes lunatus. And this seed can be from any number of genera from the Katsura family, Cercidifolaceae. However, we actually were able to identify this fruit right here as Jenkinsella. So it's highly likely that all of these seeds are coming from this Jenkinsella plant in the Katsura family, Cercidifolaceae, which today is native to Eastern Asia. We also have likely the first occurrence of Agrimonia. These are its fruit right here. They're little achenes, but they still have an attached pedicel to them that can be curved with ribbing on them, and then bristles along the apex. Excuse me. It's a little herbaceous thing. Actually, it can grow waist high, but it's an herbaceous thing, which is unusual for a fossil deposit. And then we have Celtis, sugar or hackberry, and it also has an endocarp. So this isn't a seed. This is like similar to a cherry pit. The neatest thing about Celtis, though, is that this is a mineralized endocarp. So unlike being made of plant fiber, like in your cherry pits, this is actually made of calcium carbonate. It's not mineral replacement. That is the calcium carbonate it has. This is not a tree we have, again, in the Pacific Northwest today. So if you've never seen this plant, we do have a lot in the East Coast. But if you've never seen this plant before, this is what it looks like. And then arguably, perhaps the most consequential discovery for plants that we found here is this little buddy right here. This is Thalasspi. It's part of the mustard family, and it's very closely related to Arabidopsis. And Arabidopsis is a plant that a lot of plant geneticists use in their study. And so we're pushing this date back about 5 million years. So we're pushing it, well, I think a little bit further. I think it's closer to like 7 or 8. So it's known from the early Oligocene of Montana, but now it's known from the middle Eocene. So that could affect our understanding of the evolution of this clade, an important clade for plant geneticists. We could also have the oldest quinoa. So Chenopodium is quinoa, and it makes these seeds that can be sort of snail shaped, and they can have these little notches by the hilar notch, and they can be either smooth or reticulate. So we have what we think are two different species of Chenopodium. And then we also have some new species as well. So these two are getting names. This one specifically is getting a new name because we also find it up in British Columbia as well, but it hasn't been named yet. So that's why we're giving that specific one a name. All right, so that's sort of an overview of the biodiversity of the Kichinean, at least for the flora. So now we're going to look at climate. And again, we have another big name. So bioclimatic analysis, mutual climatic range technique. So this is a coexistence approach. And so what I did was I downloaded all the occurrences of the modern living relatives from GBIF. This is the Global Biodiversity Information Facility. So if you've ever taken a picture on iNaturalist and you've uploaded a plant, give yourself a pat on your back because there's a possibility I actually use your data in this analysis. So what we have here are plots of the modern plants and their mean annual temperature distributions and also their mean annual precipitations distribution. So once we have that occurrence data, we're able to cross-reference those GPS coordinates with the WorldClim database. I then looked at it right here, and we can see that there are some weird points down here. So I ended up removing these two because I don't think anything's growing in minus 20, less than minus 20. That was probably a data entry. And then I also ended up deleting Dipteronia and Boniodendron. And that's because we only had 5 occurrences of those. These are both East Asian taxa, but if you know of them growing in an arboretum, please feel free to add them to INAT because, hey, it'd be great to have that for the future if anyone has that in a deposit. So what this technique does is that we also remove the 10th and 90th percentile. So the 10% of the total lowest values and the 10% of the highest total values. When that happens, we get these results. Again, I'll just go over a few of them. We have a mean annual temperature of roughly 9 to 12 degrees, a mean annual precipitation of 945 to 1204 millimeters. So in the past, we've thought that this climate in the Kichinean was subtropical based on the fauna that we find. And I guess it really depends on what your definition of subtropical is. Sadly, this is a word that can mean different things depending on who you talk to. Obviously, we can't ignore the animals that we're finding. But rather than having a very warm climate, it's more likely that we just have a climate that has mild winters. So when we look at the minimum cold temperature, it's never going to get down below 5 degrees. And when we're looking at the 3 coldest months and the average temperature of the lowest temperature for those months, we're getting to minus 1.4. So it's pretty mild winters. Today, this would be places like anywhere from Cromwell, England, down to Vigo, Spain. This is a picture of Vigo, Spain, and we can actually see both conifers and broadleaf trees kind of in the mid-ground here. We could be getting some bias in our answers, though. We know from geologic evidence that surrounding this lake, there were mountains. And so we could have some of the taxa like larches. Those could be growing up in the highlands, and those plant parts could be coming down into the deposit. So we might be skewing colder because of those taxa. All right, so how does all this fit together, especially since, Oregon, Montana, they're separate, far apart. These might not be the exact same age. So we're going to talk a little bit about biodiversity. And there's 3 different ways that ecologists measure biodiversity. So one is the alpha diversity. That's the number of species that you have at a site, or the abundance of each species that you have at each site. You have the beta diversity, which is the difference in alpha diversity between the sites. And then you have the gamma diversity, which is sort of the overall biodiversity of the larger region. So what I wanted to do is I wanted to look at site-wise comparison. So I'm using a beta diversity metric, and I'm using the Sorensen dice coefficient. So this is using presence absence data as opposed to abundance. Again, that's good because plant can produce a different amount of fruit or leaves, or it could be closer to the depositional environment. So we don't actually know how many plants we have based on the number of leaves or fruits that we get. This statistic also accounts for the number, or excuse me, for missing taxa. So we might not expect to find everything as a fossil between two different sites because fossil record's imperfect. And so what this does is that you have this 2A down here. So A is the shared taxa between the two sites, B is the unique taxa for site one, and C is unique taxa for site two. So mathematically, we try to account. It's not perfect, but it's a way to sort of offset something that you might not see just because you don't come across it. So the higher the value, the more similar or the more homogeneous two communities are. The lower the value, the more dissimilar they are. So this is sort of reverse of what we saw earlier. We might expect low Sorensen indices because overall the climate was warmer during the Middle Eocene. And so we usually think of warm climate means there's higher levels of alpha diversity, which could mean that there's more diversity between places. Or, we could expect higher values, less beta diversity, because a lot of these taxa had large ranges, things like tree of heaven, ailanthus, things like metasequoia. A lot of these things, today are only found in certain corners of the globe, but used to have a large Northern Hemisphere range. So again, we're just focusing here on the Lutetian. This is about 48 to 41 million years ago. Climate was going down during that time, so it wasn't completely flat. But we also don't have any of these big climate spikes like the PETM or the MECO, the Mid-Eocene climatic optimum. There is a little climate spike at the very end, but we do not include the flora that comes after that. So there's 9 different sites that we know of that are of this age, and we only used verifiable names. And so when we run the math, these are the numbers that we get. The most similar sites end up being the Kishinine of Montana and the Thunder Mountain Flora of Idaho. And the least similar end up being Chalk Bluffs of California and Princeton Chert of British Columbia. Now, we're not 100% certain on the dates of 3 of these sites. They could actually be older, going back into the Ypres, which is the stage before the Lutetian. So when we remove those 3 out, the least similar become Eckfeld over in Germany and the Kishinine. All right, so what does this actually mean? So we need something to compare it to, so let's compare it to the modern. So once again, I go back to GBIF. I download all the current occurrences for the Paleo latitudes at the time. For all those occurrences, I then round them to the nearest 0.225 degrees latitude and longitude, and I create abundance, presence, and absence matrices. I then have R, which is a statistics software, select 9 to 6 sites at random and create its own matrix, and then calculate the median and range of the Sorensen dice indices for each matrix. Now, because we can't identify all the elements within a paleoflora, we might just give it something like morphotype 1, entire leaf margin 12, weird looking fruit 12. We ended up having to, we have to delete some of those taxa because we don't know what they are. So anywhere from 14 to 72% of the taxa we also deleted at random for these matrices. And we repeated this process 1,000 times in order to try to get a statistical understanding of what was going on. So on the left are our models without deletion, and then on the right are the models with the taxa, with that 14 to 74% taxa deletion. So there are very few high values. So that means that there's less heterogeneity in the Lutetian. And most of these have wider ranges. So the spread of values is a lot wider in the modern time as well. However, when we look at just the partial data set, so when we remove the sites that we're uncertain about the age, and when we delete taxa, we actually end up getting a similar range value to what we have before. But again, this range is shifted over because our median value is different. But this could also be kind of represented because we might be able to take out some of the confining variables ahead of time. So it could just actually be an accurate model. I sort of doubt it, but that is one interpretation of it. So overall, there was less heterogeneity during the Lutetian. A lot of the floras more similar overall. One reason could be because of taxonomic richness. So if we look at this graph down here, this is species over geologic time as opposed to genera. We're looking at genus or genera before. But the same sort of relationship would hold. We have fewer down in the Eocene versus where the star is, which is where we are today. And so that could be one factor in why it's lower. One thing too, though, is that this isn't random. So our fossil sites are just where we have data from, but of course there's a lot concentrated on Western North America. But there's a lot of blank spaces in parts of Europe and parts of Central Asia and East Asia too. So it's not a truly random starting point. And there could also be community bias as well. So we don't have we don't have communities like C4 grasslands because those haven't evolved yet. And then we're also not getting things like desert plants, right? Because those sorts of things don't preserve in the fossil record. And so if there's a way to somehow take those out, that might help our modeling for how species distributions or how biodiversity distributions look like in the past versus the present. We do have these sort of contradictory terms, though. If we go back to the beginning of the talk, I was saying that the communities were different from one another in a very close space. But at the global level, that just doesn't seem to be the case. So small scale, you can get differences within the taxa that you have, but at the overall global scale, it doesn't look like that holds up, that they're still relatively similar. There can be different communities, different compositions, obviously, but overall, you're going to see a lot of those same elements. All right, so we're going to do a quick rundown of the 4 chapters that we've just talked about. So in the pollen, we've added cattails, sedges, grasses, and Oenograceae to the Clarno Formation. We've found that distance was not a factor in determining the differences that we see in those community compositions, and that they are in fact different. We've added a fern, Rhamnaceae, the family Rhamnaceae, with 2 different members in it, an Iliagnaceae to the nut beds, and we've increased the number of leaves known from the nut beds as well. Even though we can't identify the vast majority of them, we still have recognized a lot more than would have been seen in the past. We also have higher mean annual temperature estimates, unreliable precipitation estimates, and supporting evidence for an age that doesn't often get cited in the literature. For the Kishanine, we have 107 taxa. This ends up making it the most diverse Eocene lacustrine site in the US and the most diverse Lutetian lacustrine site in the world. We have several first occurrences, and most importantly being Flaspie and Agremonia, 2 new species, and we also provide the first quantifiable estimates of the climates, whereas before they were more qualitative. Finally, we see that during the Lutetian, that was a less diverse time, and this could have impacts on how we interpret the current biodiversity crisis. So in the future, I would like to continue working on some of these formations. So looking at insect herbivory or arthropod herbivory in the 2 floras. DILP, the digital leaf physiognomy, is another climate technique that we can use, and there are ways to use incomplete leaves for those, so that might be useful for both floras. On one of Steve's trips, he found what looked like could be a Pontidaria at UCMP in Berkeley from the Green River Formation, so that might be a little fun project. And then also using AI recognition technology to identify pollen, since that can be a very time-staking process that would help speed up the analysis. And of course, continuing with TikTok, I've been on a 1.5 year hiatus now from it, but I like getting that sort of engagement out there. And of course, my public outreach. And so over last fall and winter, I was helping out a lot at the Fantastic Fossil exhibit. I was the lead preparator supervisor over the weekends, and I love talking to people. It was sort of like a fossil fest every day. So, and lastly, I just want to thank everyone on the screen, either pictured or named. Of course, the Evolving Earth Foundation for the financial support. And that is it. Thank you. I'll take questions now.
I had the mic turned off, so he didn't hear you clapping. You guys want to do it? Thank you, MacKenzie. All right, so I hope you're ready for our questions.
Oh, sure. Yeah, I'm ready for questions.
Okay, I got one for you.
When
you said that this was the earliest evidence of walnuts, did you mean specifically juglans?
Specifically juglans, yes. Specifically
Okay.
juglans. Yeah.
I was about to disagree with you on that. Okay.
Okay.
The second thing is the seeds that you showed that were Cercidophyllaceae.
Mhm.
What makes you think they're Nasidium as opposed to Cercidophyllum, as opposed to Trochodendrocarpus?
So from those seeds themselves, we obviously can't tell. And I know you've done a lot of work on this family. So yeah, I know from the seeds themselves that we can't say what they are, but the fruit that we have is Jinkinsella.
Yeah, but is there any evidence that there is Nasidium there?
There's no evidence of Nasidium. We just have the Jinkinsella. So I mean, it is possible that we have another cercidophyllaceous plant that's producing the seeds as well, but we do have that Jinkinsella fruit. I can probably put the...
Yeah, that's okay. I know what it looks like. I've seen all of those seed morphologies in the Joffrey plant, which is
right.
Paleocene from Alberta, which is not that far away, but yeah.
Right, exactly. Yeah.
Okay.
Yeah, but yeah, that's why. So we still have in the...
I wouldn't do it Nasidium, because Nasidium is coming out of Europe, right?
Right.
I don't know anybody that's actually proved we have Nasidium in North America at all. But we do have Joffrey, and we have Cercidophyllum like plants that maybe we don't know what they are.
Okay.
You have to have the attachment bits in order for you to tell what you've got. So
right.
Just a cautionary.
Oh, so I guess to clarify then so Jinkinsella wouldn't necessarily be
Jinkinsella is just a name for fruits that look like that.
Gotcha. Okay.
It gives you no information at all about what plant it came from other than the family, right?
Gotcha. Right. Yeah. Okay, now I see. All right. Thank you for the clarification.
Yeah. You got something?
Nope.
No.
All right. No, I don't have a question. I do have a comment though, and that is that you've done a very fine job with that.
Thank you.
You are to be congratulated. You can also congratulate Steve for pointing you in the right direction.
Thank you. I'll do that.
Yeah, well, I was going to ask him something else too. I forgot.
Anybody out here want to ask? There's about 30 or 40 of those vocabulary words. You want to go back and explain to us what they mean?
I'd be more than happy to. I mean, if you know what they are, or remember like what picture was on the slide, I can pull them up. I mean,
no,
yeah.
No, I was mostly being facetious, but I guess my comment is that's why it's a PhD. Right? So our hats are off to you, MacKenzie, for learning all of this and being able to construct it in a meaningful fashion that's going to work for a PhD level understanding. At some point down the road, I bet you could find a way for a general public audience that knows what fossils are like we do, but doesn't quite get the particulars of how all of it fits together in the ecosystems of the past.
Right. Yeah. And part of the problem too is there's just so many plants in a lot of these localities. Like I said, I think Steve and I thought there were only going to be 15 different plants from Montana, and there ended up being 107. There's actually still some more that we just didn't have time to get up, and so that'll be we'll get to those when we look at herbivory.
Harold Hines here. I got MacKenzie. I've collected as the nut beds, so
Yeah.
I've got a couple quick things. Leaves are very rare in the nut beds, correct? And I noticed how fragmentary the evidence you have. There's hardly a complete leaf in the bunch. That must have been a real problem in terms of interpretation.
Yeah, so exactly. So that definitely makes the interpretation hard. I know Steve and a lot of volunteers back in the 80s spent a lot of time just gluing the leaves back together. So during the OMSI camps, he would take the students out there, and there was a lot of time spent into gluing them. So you'll see, in our drawers, we actually have 2 full cabinet drawers of leaves. So there are, I mean, granted, they vary in size. But as you're saying, it is hard to find a full leaf. And yes, so there is some bias in the small leaves. So it is easy to preserve a small leaf, but some of them are large, and that's when they get fragmented, and it's a weird, you've dealt with the sediment before, it's very tuffaceous, and some of the leaves are all wrinkly and warpy, and they crumble. So
I have
absolutely.
a second question. Dr. Bone's collection of seeds, how do they figure in your work?
So I have just a basic comparison of what we have from like stuff that Dr. Bone has collected, from the woods, and then from the pollen and the leaves. So it's just a simple table of what taxa do we know from this family, and it's done by family. So that collection, of course, is down here at University of Florida. We have a special cabinet just for that.
One more.
All right.
You said you had Spirodella, and you know it because I didn't understand what you were interpreting as those specks.
Yeah. So I'm interpreting those specks as what are called brown pigment cells. And
could they be trichome bases?
I guess they could be. I hadn't thought of them as that.
Well, think about something like limnobiophyllum or Cobania or all of those other things that are floating aquatics, small leaf floating aquatics that are in the fossil record, that do have all the little specks that we see are actually hairs, right? Trichome bases, right?
Okay.
So they're hairy leaves, right?
Right.
So I don't know that was Spirodella at all. I couldn't see by any means how you have to have a centrum, you have to have the roots, you have to have a lot of other stuff, I think, to identify that as a Spirodella.
Okay.
And also your Wolfia, I don't know.
Okay. Well, Chris West wasn't sure about that either. So,
yeah, I mean, I don't want to say what I think, but I do.
Okay.
I don't believe it.
All right. We can talk about what it could be later. Yeah, that was just something. It looked similar enough, and I'm just like, it could be. So, but yeah, definitely willing to concede that it isn't. So,
yeah, don't feel badly about it, MacKenzie. She's a tough critic. I should know.
I know. Well, I mean, that's what makes science, good, is that you do get the criticism and the feedback to make it the best it can be.
This is your pre-feedback, so when your committee grills you tomorrow, you'll know what to expect.
Right.
You never know.
Yeah.
Yeah. Interesting. Yeah, I was just kind of comparing, like I was talking just a couple of weeks ago at the British Columbia Paleontological Association meeting in Victoria.
Yeah.
And we were talking about the flora from the Appian Way, which is also supposedly Eocene, but they keep changing the dates on it to be maybe a little older now, maybe Upper Paleocene. So there's a lot of conflicting signals into actual age of it, but it has some taxa in common with the nut beds. Like that Tiffany carpa and other things. I mean, it has Juglandaceae, but not juglans, but it has extinct Beardia and other things like that. And so I think the nut beds is a bit young compared to, but you're going 48 million now. I think we're moving ours back a little.
Okay.
Yeah, so it's not exactly equivalent, but there are some taxa in common. And also, also the London clay, right?
Right. Yeah. Well, I think that's still Ypres, if I'm not mistaken, right? That's like 50-ish million, or is that younger now?
Well, older maybe. The London clay
Okay.
floors go Paleocene, Paleocene to lower Eocene, right?
Yeah.
So there should be some taxa in common there as well.
Right.
With what,
Right.
so yeah, totally. These things are not very specifically dated.
Yeah.
Yeah, we have no volcanics or anything nearby.
Exactly. Yeah. It's hard for that. So.
Yeah.
And the different critters are aged differently.
Right. Totally different land mammal stages. So.
No, and
European land mammal stages.
Yeah, and a lot of the different invert groups are different too.
Right. Right.
Not changing the subject, but altering this to slightly different path. When you do your defense tomorrow online, would you have guest experts like Ruth and Gar observing and being able to ask you questions? Will you get asked questions by people that are not necessarily directly related to your research there?
Of course, yes. So the defense is a public event. So anyone from the public is allowed to show up to and that's, I mean, I would open up to the public anyway, but that's the university policy as well. So anyone can come in with any level of expertise. And so it's not only my committee, but it's probably some people from the department and the museum are going to show up. And then of course, friends that I work and do research with are going to be there too.
And then they put you in behind the scenes after that. They cut off the camera and the committee only will ask MacKenzie questions.
Okay, so do you practice, MacKenzie, with some of your colleagues, not just like tonight, but prior to this, getting thrown like curveballs and things like that? Is it that kind of serious, or is it more or less just more a discussion? Are they trying to find out if you know the material to defend your dissertation, or are there specific things that you have to be prepared and you know it and they know it? Do you understand what I'm saying?
Yeah, no, I think you got it the first time around. That you're actually defending what you know.
Yeah,
So
and can you think on your feet? How well do you handle questions? Are you going to tell them all to bugger off or something? Can't do that and expect to pass.
Yeah.
Well, MacKenzie, for somebody who's been through a PhD defense, it is more of a celebration than an inquisition.
Okay, that's kind of what I was thinking. It's kind of in the bag now, or are you nervous about this?
I mean, honestly, I'm actually still a little nervous about it, just because I just want to do my best. And I think it's just the unknown. Like I hear things from people. I know it's going to be okay, but yeah, I would still say that the nerves are still there for the after part, and not so much for the presentation. That I can do, but it's just sort of like what happened in the room where it happens, to the Hamilton song. So
yeah, fantastic.
Well, think about it this way, MacKenzie. If you don't know more about what you're talking about than everybody else in the world put together, you don't deserve a PhD.
Right. No, and that's the those are the intrusive thoughts in my head.
but from what I hear, you do.
That's good.
You're a good
I like your sources.
Okay. Question.
Yeah. MacKenzie.
Hey, Robert.
On one of your slides, the one that showed all the dates of the sites, I think the date for the Arbuckle Mountains is wrong. It's too young.
Okay.
It should be more older than 45 million.
All right.
I think I know where you're getting that date, and that date is definitely wrong.